Thank you. I'm Gabriele Marra, and this is a paper that I published and I presented at SpaceX in San Diego last month. So that's what I'm going to talk about. Well, from most of the talks that we had today and also yesterday, we already know that the number of satellites in orbit increased by thousands. Now we have 10,000 or even more satellites. Most of them, a lot of them are actually developed by startups, universities, and they don't care and they don't have the resources to think about security. And also we can see a slightly, but still fast shift from FreeRTOS or real-time operating system to Linux. That's basically the landscape where my research and my paper is actually placed. The other place, and the reason why I did this research is the Raccoon project. What is Raccoon project? Is a project from the Technical University of Berlin and multiple commercial and institutional partners. They are developing a system to deploy and transmit security keys for post-quantum encryption algorithms through small satellites. When developing and starting designing this project, we figured out that well, we can have the best algorithm that we can have, find from open source and competition, etc. But if we don't have a robust and secure OS, then it's useless. That's also why we started the Raccoon OS project. It's a new security-focused and open source OS that we are developing right now. It's based on Linux with Yocto Linux and on Robot Operating System 2. And the idea behind is that we use Rust to write most of the application and most of the components, and the entire stack will be open source and hopefully, but that's what we are targeting, a really secure and modular operating system. Why Linux? Because a lot of the new hardware that we are starting to see in space and even in small CubeSat can run Linux, maybe ARM devices or anyway enough powerful to run Linux, and also we can use a lot of the security features that comes with Linux and have a easy way. This is a small overview of the Raccoon OS architecture. It's relevant to the entire mission and the paper. On the side, left and right, you can see our communication interfaces, the one with the satellite itself, because the Raccoon project will be a payload on another satellite, and our own communication interface on the right. And the most important part and the most important nodes and components are those two. The master node that will control all the other nodes and application, and the quantum or key experiment and key algorithms that will contain and store and basically manage the entire keys. And the approach and the threat model that I identified and we are currently using for the entire mission is that we are going to have, of course, different level of authentication, and only authorized user can access the most important application, and we don't focus too much on untrusted code because we are going to write our own code, but maybe it could be vulnerable. And what we want to achieve is basically every single component inside our software is going to be isolated. We would like that it's going to be isolated and cannot interfere with other components to avoid lateral movement. Well, when I started my research, I started from the basic. What are the already available tools that I can use to achieve that result, to contain and do not allow other applications to interfere with others? Well, you can use hypervisors and virtual machine, you can use containers, and you can use application sandboxes. I actually choose the third one because it's a good mix between isolation and performance. Why not hypervisor or virtual machine? Well, they're really good at isolation, but also the overload is higher. And not all the components that we're using for CubeSat can actually run and support hardware, doesn't provide hardware support for virtual machine. Containers, on the same hand, it's still a good trade-off for isolation and performance, but are more oriented to deployment. And even if they come with a lot of security features, recently with Docker, still we decided to go with the sandboxing. What does a sandbox with Linux? It uses a lot of security features already offered by Linux, like Linux namespaces, croots, and also most important, second BPF filter. So it allows us to filter some particular system calls and only allow what the application and the program that we want to run inside the sandbox actually need. Also, I try to understand what are the other threats that we have in space that in a normal embedded system or like computer we don't have. And of course, the satellites need to be autonomous. Most of the time we don't have connection. We also need, we have operational constraints, and also really important is a single event upset, because in a configuration like ours, if something goes wrong with the configuration files or the configuration of a sandbox, it could be a problem with recovering the mission. So I didn't focus too much on that. I decided to just use ECC RAM or FRAM, not like less to avoid this, and also a file system with forward correction. Then a list of the cybersecurity threats that I consider: trusted inputs, lateral movement, denial of services, and finally I started doing the analysis. What I found is that I found 3 sandbox tools that are interesting: NSJail, FireJail, and BubBubWrap. And then I consider also 2 mandatory asset control systems, AppArmor and SCLinux. I also considered other sandboxing tools, but they were like kind of like projects not available, not developed, and so we just discarded them. A little bit more information about what I found. For example, NSJail is originally developed by Google. It's not an official Google product, but it's developed by Google engineers for running CTFs. And then it moved to a more generic, like sandboxing approach. And then FireJail, it's really good for running and sandboxing desktop application. And BubBubWrap instead is used by Flatpak to provide isolation inside the Flatpak programs. Instead mandatory access control, we have AppArmor and SCLinux, really good at like managing which file you can access and which not. But they are kind of not really what we were looking for, and also not easy to implement and deploy, and so we actually decided to not select those. At the end, I moved to a more comparative analysis. Don't worry, I'm not gonna read everything in this table, kind of complex. I just want to emphasize that BubBubWrap on the right doesn't meet the requirements that I identified. And also FireJail seems promising, but then when you look, it doesn't come with, you need root access and like privileged execution in order to run FireJail. And in our opinion, it's not a smart move, because if there is a problem with the configuration or inside FireJail itself, then maybe an attacker can exploit that, and you already provided root access, and so basically you are helping it. And that's for this reason I actually choose to use NSJail. What I done later is try to test if all these features promised by the documentation are actually present. I did some scripting, and also I developed a small tool. It's open source, so you can look it up. It's basically check if the configuration is corrected, like it prints whatever the program can see, the details, how the configuration and the sandboxing works. And well, now I have this nice tool, supposed to be working. It works with standard binary for Linux. Can it run space framework, Space OS? Well, that's what I wanted to figure it out. Unfortunately, the Raccoon OS, for the same reason that we like the reason why I started to do this research, is not like enough mature to be tested and to be useful in this testing. So I had to find something similar. I identified that since we are using ROS as a middleware, I need to find something that resemble the same architecture, and with publish and subscribe mechanism or client server. What I found is those two open source projects, the CySPA software and the CySAT IPU software. Both of them resemble somehow the middleware-like architecture, and open source running on Linux, so perfect for my testing. The first thing that I found out is that I was able to run both of them inside Linux. This is a kind of a spoiler of the takeaway, is that already existing firmware can run pretty easily, just a couple of days of setting up and configuring everything inside a sandbox. So maybe for already deployed space mission could be, and like maybe only small modules that are more exposed can be interesting. This is a small overview of the CySPA software. What is important, it's on the right. It's basically use CubeSats-based protocol and 0NQ to create a sort of middleware-like architecture. And what I did is basically I created this setup with Linux, then I installed on top of CySPA software and the NSGL sandbox. And I configured the sandbox to use croot, read-only bind mounts, namespaces, and SecondBPF filter to basically allow only the system calls that are required by the CySPA software. Everything else is blocked, and the setup is actually to the policy is to kill the application if anything out of the ordinary happens inside the sandbox. Then I introduce a command injection vulnerability. So I deliberately introduced this vulnerability to test if I decided to, like, if an attacker found an exploit and try to do like an operation that is not allowed, theoretically allowed, what happens? Well, without an SJL, you can immediately get shell access and access to the unauthorized file. So what happened is that our secure keys for the best algorithm encryption, well, like an attacker can gain access to those. Instead, with an SJL, the process is getting killed, and so the data confidentiality is preserved. This is really important for our own mission, and it's actually better to kill, like in our idea, we discussed this through, it's not an easy choice, but we actually decided that instead of losing the keys, for example, an attacker can steal the key and then recover and decrypt the messages, well, it's actually better than the entire mission fails. So that's why you see process killed. A lot of system engineers will like panic now, but hopefully no system engineers here. And this is the CySAT IPU software. It's pretty similar to the Raccoon OS architecture. As you can see, they are using ROS1 and we are using ROS2. What you can see is there are different nodes and it runs also Linux. I basically did the same experiment. I use an older version of Linux and also an older version of NSJL, but still provided all the functionalities. And I introduced a new the same vulnerability, something similar, inside the execution node of and the command parser node of the CySAT fly software. And the result were exactly the same. Without an SJL, you can access the files. With an SJL, the process again gets killed and the data confidentiality is preserved. There are still some like challenges integrating NSJL inside Raccoon OS. First of all, right now I need to, like the way we did for also running these tests is that I call NSJL through the terminal. Well, we can't access the terminal or have an SSH connection into the satellite, so not suitable. I found two possible solutions. The first one is to refactor NSJL as a code library, and the other one is invoking the NSJ binary directly. The first solution is actually being discarded because then somebody needs to maintain the new code library version, and then we decided to then invoke the NSJ library directly, and we decided to create a wrapper that handle also the configuration files. In this way, we can have NSJL, we can have our wrapper that calls NSJL with the right configuration file for every single binary inside the that we want to sandbox. Also, we identify multiple strategies. For example, we thought about, oh, we put every single node, every single binary inside a single container, or maybe if we don't want too much overhead, we are only worried about untrusted input for the COM. Like, okay, let's put every single new command received, it's parsed and analyzed and run inside a different sandbox. That's also a possibility. We still need to understand which one of these solutions is better. Both of them seems feasible at this stage. Hopefully, we can actually decide later. Well, that was the end of my talk. I also want to add a little bit of takeaways. First of all, as I already mentioned, this NSGL tool and other sandbox tools that I may have discarded because for our mission requirements are already existing and are currently developed and supported by multiple open source contributors or even companies. And I actually think that some of them can be useful in space mission. Future space mission, you can integrate them inside your in your design phase, or even already deployed mission that doesn't have too much security. Maybe you're already found some vulnerabilities or you're worried. You can maybe try to find and run those on your like engineering model on Earth and maybe understand, oh, that's actually a nice idea. And the other one is Raccoon OS. We also have a boot. Maybe you can buy later. It's still not it's available right now. We're still working on the first release, I would say, but I think it's going to be an interesting project, having a really secure operating system available for everyone to use in satellites. Well, thank you for listening.
Thank you, Gabriele. That was a really nice talk, really interesting about sandboxing. I have experience with containerization, but nothing about sandboxing, so that's really nice. And we have some questions coming in. So from John, how complex is it to set up the sandbox jail? For example, the satellite that you set up, how long did it take? How difficult was it?
Okay, it really depends on how the software works. For example, for the Suchai software, it was easier than the CySAT one. It took me like a morning to set up, like in somehow running way. What also we are like still planning, we're not sure if we can do, but I think it's feasible, is to also like create a tool that basically is similar to the sandbox, but it's meant for the developer of the single application of or the entire operating system to run the application inside, and at the end the tool will provide a nice configuration file already only for the allowed application. Because when you develop a software, you know what the input that you're expecting, and so you can basically it's basically the opposite of the fuzzers that we listened to like a couple of talks ago. You know what you want to receive, and so you test, and you at the end like the tool should provide a configuration file, or at least a sort of guidelines which libraries you are needed, how to create the C root, and which syscall are actually needed. So yeah, that's the idea.
Thank you. And another question from John. Let's see if I get this right. So the example satellite that you hosted, the example system, how complex was it? How complete was it in terms of subsystems it contained?
Both, okay. The Suchai Fly software, it was a fully operating system for satellites. It's actually like running right now on 2 or even 3 satellites deployed by the University of Chile. Of course, there are CubeSats, so like not super advanced, but still like they have a lot of sensors, some science mission on board. And instead the CySAT software was only for a payload, for a few sensors and a camera, I think. So it was less complex, but still representative because of the robot operating system one, and so the architecture was kind of similar.
And how did you connect to the satellite system? Was it just SSH?
Well,
or?
in this case, I tested on like virtual machines or embedded device that like I had on my desk. So right now it was still like an experiment again, but still, since I don't work with low-level interfaces, it should be like a proper testing is actually needed, but like should be feasible.
Thanks, and thanks, John, for interesting questions. Any questions from audience? Oh, okay. Let's start from there.
Hi, Wouterloo from the NLR. Thank you very much for your presentation. It was very interesting. Are you planning to do any performance tests and release that to the public?
Yes, I already tried to do some overhead analysis, but since I was running inside the virtual machine, it was not representative. From what I saw, the overhead was minimal, but again, it was. I think there is a small overhead, but should be enough. Like the value that this provides should be more than enough to compensate for the overhead. But still, like no, you are completely right. Like it's.
And it would also be really interesting to see what the effect of this will be on the robustness in the sense of single event upsets and stuff like that.
Yes, I think I mentioned in one of the first slides that I wanted to use FRAM or RAM with ECC and also file system with forward correction. The idea,
that helps,
yeah. The idea is to use those file system and those like solution to store the configuration files. So even if in event of a like single event upset, if it happens on the RAM, maybe kernel just like is not just, but like it's a reboot and you should be okay. If it happens on the configuration file, well, there could be a problem if you don't have any way of recovering the file. But with forward correction, it should be, or FRAM, you're less like vulnerable to this kind of event.
Great, thank you.
You're welcome.
Thanks. Next question, Mario.
So great presentation, thank you, Gabriele. So my question is about the, is there a way to do like pass-through hardware, or how you handle like devices if your binary need to access the device? If it's something that you can do, or is something that you can?
Yes, inside the configuration, you can allow specific access to devices, and yet, like since I only tested in a small experiment, I didn't have a fully satellite, fully test bed to actually test it, but it should be like feasible and interesting. Like.
Okay, so you have it in the configuration, say you can access only this device or this.
Yes,
okay.
You can specify which devices, which folders, which files you can access, and also the syscalls and namespaces. You can lock everything. You can basically have something really light. Also, I think, also to answer that question, the overhead may depend also on the type of configuration that you set up. You can also set up a C group. Like policy. In this way, you can also avoid denial of services, maybe.
Awesome, thank you.
Next question.
Hey, so I may have missed it, but you mentioned some of the negatives using Firegel and bubble wrap. Are there any negatives using NSGel?
Well, like you mean the comparative table?
Yeah, or anything else that may not have been in the presentation.
Well, I think that NSGel, it's pretty robust and valid tool. One of the downside was that there is no support for logs for unauthorized file system access or attempt. What happened is that for my attempts, when I was trying to access like files, I was actually unable to access those files because I was inside the C root. There was the only allowed bind mounts, but from the outside I wasn't able to detect that. So it could be interesting to like maybe see if it's possible to do a pull request and add this functionality to NSGel itself. I think it can be also interesting from the point of view of the NSGel itself, but still, like this is one of the only downside. If I actually go back to the slide, it's the only one that is yeah, here. logs file for fast evaluation. NSJ, FireJail actually provide that in functionalities, but not NSJ.
Okay, thank you.
Any more questions from the audience? All right, here we go.
Yeah, thanks. Hi, thanks for the presentation. Well, yeah, can't containerization also provide sandboxing capabilities and with ease of deployment and configuration?
You mean like Docker?
Yeah, and Podman, for example.
Yeah, Docker and Podman. As I mentioned in like their presentation, I spent a significant amount of time thinking about using Docker. I wasn't like I actually ended up using NSJail because while I was I think it's also like a choice, a personal choice, but the idea behind Docker is still like easy development, easy deployment. It provides a lot of security features, but also is not the security feature is not the first main goal, at least from like my understanding. And also, like I wanted to provide like the lower overhead possible, and still Docker doesn't run like it doesn't emulate or virtualize the system, the kernel space, but still the entire user space is virtualized. So,
Thank you. Any more questions from the audience? If not, I have one. So you did mention that the systems you tested on, they use ROS as middleware.
yes.
And ROS has been gaining in popularity quite rapidly in recent years, especially ROS 2. And I was wondering how much of your research is applicable outside of space sector just to ROS-based systems.
Well, that could be an interesting question. I didn't think too much about that actually, but I guess that if a ROS node for space works in like inside NSJail or other sandbox tool, actually I think I also tested some of the other bubble wrap and FireJail, and I was able to run some node inside them as well. So could be interesting also for this reason. Anyway, yes, I think it could be interesting exploring that and. I don't know, maybe in a few years, ROS2 will ship with support for sandboxing specific nodes, maybe the one that receive untrusted inputs or sensors, and so that could be an interesting idea that ROS developer can maybe explore.
Might be your pull request that brings it in.
Or my pull request, yeah.
Thank you. Give it, everyone, to Gabriele.